Episode of Science Never Sleeps. Here we're going to be proving the mass flow rate in equals the mass flow rate out in this bucket problem. Here, a hose will fill up a bucket with water, and there will be a hole at the bottom of the bucket that's letting the water out. Now, to prove this, we're going to let the mass flow rate in equal the volume flow rate times the density, as seen here. Now we can find the flow rate by finding the area or velocity, or another way is we can find the volume and find the time, how long it takes to fill up that volume. We did that by calculating the volume of this cup and timing it on a stopwatch. And I got about 4.38 seconds on average. Now, for the mass out, we're going to have density times pi over 4 times the diameter squared over the square root of 2 times gravity times the height of the bucket. This right here was derived from the problem that was solved. Here, the two densities can cancel out, and then with a little reorganization, we can have the flow rate is equal to pi over 4 times diameter squared times the square root of 2 times gravity times the height. Now, first, after finding the flow rate, we are going to select an arbitrary height of 15 centimeters. With that, with using this equation, I was able to find that the diameter would need to be that wide. Now, since this is in metric, I need to find an imperial size hole. So, I found that the closest was 932, or a diameter of 0.007125 meters, which resulted in a height of 15.8 centimeters. Here in these, the squares show with the selected H, and the triangles show with a selected diameter. Now to check, I use the solution manual, or the solution of that quiz, and I plugged it in here, which I got the same number. Alright, so here we can see that the water level is staying around 16 centimeters. This right here proves that the height is staying constant. With that height staying constant at 16 centimeters, we can determine that from our results that there is an error about 2%, meaning that is successful. We have proven that this H is true. Now plugging into this overall M in equals M out, we're able to see that the flow rate from here equals, or close enough equals to each other. There is only about 0.5% error.